My presentation is on the paper titled Adapting Pre-Trained Vision Language Foundational Models to Medical Imaging Domains. My name is Justin Trout, and to give a little bit of information, um, as I mentioned, the title, and there are 4 authors, and these authors are all at Stanford University, specifically the Center for Artificial Intelligence in Medicine and Imaging. And this paper is addressing a problem of there being a paucity or scarcity of medical image data. And in addition, this paper wants to create realistic medical images better than current state-of-the-art generative methods. And in this context, a generative model would be generating medical images. And as mentioned in the title, this paper deals with foundation models, which they mean a foundation model to be a stable diffusion model pre-trained on large amounts of data. And it's a model that's intended to be very generalizable. As you may know, but to define a pre-trained model, it's often a neural net that's already been created by others to solve a problem and has layers and connections that have already been fine-tuned to do well on that problem. Let's see. So this paper wants to adapt pre-trained models to medical images. Specifically, this paper wants to adapt the stable diffusion model published by Robach in 2022. And it wants to take a stable diffusion model that's a foundation model trained on a large data set of natural images and fine-tune this model to be good at generating accurate and realistic chest X-ray images. And the paper fine-tunes subcomponents of stable diffusion, including the variational autoencoder, the UNet, and the text encoder. And then there's some related work to this paper, like in 2022, diffusion models for medical image analysis, a comprehensive survey, and also Diffusion DB, a large-scale prompt gallery data set for text-to-image generative models. Also, there's, in the medical domain, unified chest X-ray and radiology report generation model with multi-view chest X-rays. The impactful paper by Rombach et al., high resolution image synthesis with latent diffusion models, where I believe they introduced diffusion, latent diffusion, and then photorealistic text-to-image diffusion models with deep language understanding. And as mentioned earlier, there's a little bit of a scarcity of annotated and labeled medical image data. And also non-fine-tuned stable diffusion does not always generate the most realistic or accurate medical images. And this paper would like to generate even better, more realistic medical images, and also more realistic abnormalities or disorders in those images. Here you can see some images from this paper. On the left, you see stable diffusion that has not been fine-tuned or trained on that has not been fine-tuned for medical image data, specifically not been fine-tuned for chest X-rays. And on the second image from the left shows what this paper created with fine-tuned stable diffusion, which they think is a higher quality image. And then the two images on the right are show a similar comparison between non-fine-tuned and fine-tuned stable diffusion. And on the right, the two images are meant to show an abnormality as well, not just a healthy patient. And I suppose the motivation has somewhat been covered, but essentially they want to improve image generation in the medical domain. And so some of the main contributions of the paper are they found that their best performing model generates chest X-ray images that are an improvement on the stable diffusion baseline. And they found that these models can be conditioned to insert a realistic looking abnormality on a synthetic radiology image. And when a classifier to detect this abnormality is ran on synthetic images, they classify the synthetic or abnormality in the image with 95% accuracy, indicating that a classifier can detect this inserted synthetic abnormality. And the approach outline, this paper used two separate chest X-ray data sets. They conducted five experiments, each one focusing on one component of stable diffusion while holding the other components constant, not changing those components from how they were in the Rombach 2022 paper. And the first experiment assessed how well the variational autoencoder can reconstruct chest X-ray images. I'll explain that more in a minute. The second experiment assessed text encoders. The third assessed what they termed textual projection. The fourth assessed textual embeddings, fine-tuning, and the fifth assessed fine-tuning of the UNet. Getting into the specific data sets, the first data set was called the Che expert. I'm not sure if I'm pronouncing that correctly, but their chest X-ray data set from Stanford Hospital. And the second data set was the Mimic chest X-ray data set from Beth Israel in Boston. Let's see. So the initial diffusion model was just trained on a large multimodal data set, meaning both image and a caption for the image. So image and text being multimodal, which had natural images, which were just images of, I think, different things in nature and not anything specific to the medical domain. Let's see. And I'll just move on to experiment. The variational autoencoder. Essentially, what it does, in brief, is it takes an image and it somewhat it takes it sort of isolates compressed features from that image, and then from those compressed features, it can generate a new reconstructed image. And this first experiment wanted to see how well the variational autoencoder could reconstruct an image from these compressed features called the latent space, and how similar that reconstructed image is to the original image. And I'll get into the metrics used to compare the reconstructed image to the original. Let's see. Some metrics that were looked at were root mean square error, peak signal to noise ratio, structural similarity index measure, and a metric that was used always to compare a reconstructed image to its original. So comparing pairs of images is the Frechet inception distance. And that was sort of a main metric used throughout the paper to compare one image, like an image created by a fine-tuned diffusion to an image created by the original diffusion model. And then lastly, in addition to quantitative metrics, there was a radiologist who inspected the pairs of images and had a rating scale from 1 to 5 on how similar the reconstructed image was to the original. And then in addition, in this experiment, a pre-trained dense net was used to try to classify abnormalities or disorders in these reconstructed chest X-ray images. There were 18 different disorders that occur in the chest that this dense net was meant to try to classify. And some metrics were classification accuracy, area under the receiver operator characteristic curve, the F1 score. And then in addition, the sort of latent representations of both the original image and the reconstructed image in the intermediate layers of this dense net were compared with pairwise cosine similarity. Now moving on to text encoders. This paper looked through the literature and previous pre-trained models and found 6 different text encoders that they wanted to compare to this the stable diffusions text encoder. Here are their names here, and there was also the clip text encoder. And what these encoders do is they take a radiological free-form text report, which will be many sentences, and they try to extract text features from that. And those text features will then be paired with that image. And if you have a better text encoder, it can extract more important features from this radiological text report, more important or better captions to match the corresponding image. The images also all had abnormality labels from the Che expert labeler model. And to compare the quality of these 6 different text encoders, the paper came up with their own metric called the Che expert at K metric. And for these radiological reports, the metric looks at the K. K could be, say, 10 most similar reports, and it looks at the proportion of these reports that have the same Che expert abnormality class label. And this is used to sort of determine how well these different encoders extract the correct features from the text. The another experiment was textual projection, which they also called textual inversion. And this replaced the clip text encoder with a medical domain specific text encoder, with the hope that a medical domain specific text encoder could better capture a good caption from the radiological report. The clip text encoder was the encoder used in the original Stable Diffusion training. And another experiment was fine-tuning the textual embedding, which is separate from the textual encoding. And this in this experiment, the variational autoencoder mentioned previously, and the UNet and other components and layers of the text encoder are kept frozen, kept in the original Stable Diffusion settings. And this experiment introduced tokens which code for patient level features, procedure level features, and abnormality level features. So it sort of introduces new features into the text, and it zeroes out the gradients of existing tokens. And this was trained with the Stable Diffusion model was trained with input prompts from these new tokens, and images were generated based on these captions from these new tokens. And then these images were compared to other images using the Frechet metric mentioned earlier. Another experiment was the UNet fine-tuning, where all components of the Stable Diffusion model except the UNet are kept frozen. And mean squared error loss was used several times in the denoising process. And this was meant to generate hopefully more accurate chest X-ray images, which were then compared to images from the untuned UNet model using the Frechet image comparison metric mentioned earlier. Results, they found that the clip text encoder had better performance than 4 out of the 6 domain-specific text encoders. They found that the UNet fine-tuning generated images visually and quantitatively better than the unfine-tuned UNet model. And there had not been a previous study exploring Stable Diffusion to generate chest X-ray images. And this was also the first study to systematically explore Stable Diffusion pipeline for medical images. Also, there have been previous research using Stable Diffusion to generate brain MRI images from simple labels. But this study, which was multimodal, used text captions to generate images, which can be more than just a class label of disease or no disease, but can include all sorts of different text captions from the radiological report. This paper found that they could create, with their model, high fidelity, realistic medical images, and also realistic abnormalities. They found that their model lacked diversity in the images it generates, possibly due to limited training data. The textual projection which they also call textual inversion, was unsuccessful. They did not manage to create realistic chest X-ray images from their textual projection captions. And also they found that it was difficult to distinguish between abnormalities in this textual inversion or projection experiment. And then lastly, the text used in the experiment was perhaps simplistic and can be unlike clinical text and may not capture all the information from the radiological report. I gave this paper a rating of 1. I thought it was a very good paper and it made a couple notable contributions, creating high fidelity medical images with realistic abnormalities. So it has they provide a sort of a proof of concept for the idea of fine tuning a stable diffusion model for a specific domain like chest X-ray images. They fulfill a need for more annotated medical data sets, which can be used as a data augmentation. And textual projection was unsuccessful, and they found that the texts that they did not really use, they could perhaps use more sophisticated ways of extracting feature from radiological reports, and the generated images lacked diversity. Future directions, I think they could work on greater image generation diversity, possibly by using more training data and more varied training data. Expand this approach to other medical image domains other than chest X-rays, perhaps other organs or other imaging modalities like MRI, and also explore different diseases. They could also, with their text, use more clinically realistic prompts and look at more chest X-ray data sets. And here are my references. Thank you.